Okay, in this chapter, we're going to discuss several different topics about ordinary least squares estimators. Okay, the first topic we're going to talk about is heteroscedasticity. So what is heteroscedasticity? Heteroscedasticity occurs when the variance of the residual is not constant across observation. That is, suppose you have the model yi equals xi beta plus ui, or as we saw, we could write it in matrix notation in this way. Before we assumed that the variance of the error term is the same, so it doesn't have an I subscript. However, in some applications, and we'll discuss some of the applications later, we might have reason to believe that the variance varies across observations. Okay, so with heteroscedasticity, we want to allow that e of ui squared given xi equals sigma squared I. So it's basically just a more general assumption on the error term, on the variance of the error term. Okay, so let's look at the variance of the OLS estimator when ui is heteroscedastic. Okay, under homoscedasticity, the variance formula that we had derived earlier looks like this. Okay, and then the estimator that we had looked at earlier was this. So this is just the estimator for these objects, where sigma squared is estimated in this way. Okay, now compare what variance expression do you obtain if the error terms are heteroscedastic. Okay, so to get this expression, you probably have to look back at the previous lectures, but we had this expression before, and before we had assumed that e of ui prime given xi equals sigma squared I. But now we're not going to assume that, we're going to assume that this equals some more general omega matrix. And omega is a block diagonal matrix. Okay, so omega is going to be this matrix here. Okay, and we can estimate this variance, by this, it's not going to be obvious exactly why this is the estimator. There's actually a paper by McKinnon and White that it's an older paper, but they actually suggest multiple different ways of estimating the variance when you have heteroscedasticity, but this is one of the approaches, and this is probably the most common one. So this is what you'll often find programmed into some software packages. Okay, so this is the usual x prime x inverse matrix, which is of course easy to calculate. This here is the x prime omega x, where we're using the fact that the omega matrix is block diagonal. So block diagonal means it only has non-zero elements on the diagonal, right? Everything off of the diagonal is zero. So we're using that structure to write the x prime omega x this way. Okay, and this is called the robust standard error formula. It's also called Eicher-White, or I think there was another paper by McKinnon-White. Okay, but if you use like Stata, and you invoke the robust option when you use regression, it'll be doing this formula. And it turns out this formula would also be correct even if the error terms happen to be homoscedastic. Okay, so in some sense you can never go wrong by using this formula if it's heteroscedastic or it's homoscedastic. That's why it's called robust, because it's more robust than just imposing homoscedasticity. Okay, so occasionally you might know the form of the omega matrix. So as an example, when you might know the form, one instance where you can have heteroscedasticity is when the y and the x's represent means. Okay, like suppose that you run a regression of the mean crime rate in a state on the, average amount spent on policing resources. Okay, where this is a mean and this is a mean. So with means, you can have heteroscedasticity just because different sample sizes are used to derive the mean. Okay, so that's an example where you could have a known reason for the heteroscedasticity. Okay, so suppose that, and in that case, you don't actually know the sigma, but you might know, here in this example, I'm assuming you know the sigma, but even if you don't know exactly the sigma, you might be able to undo the heteroscedasticity if you know how it varies with n, okay? But anyhow, for now, assume that you know the sigma. So look at what happens. If you knew the form of the heteroscedasticity and you divide everything by sigma I, okay, and just call that yi star, so we just divide it through by sigma I. If you look at E of ui or u star prime given xi, this is going to be I, okay? So that tells you that you've basically undone the heteroscedasticity, okay? And you can apply the usual variance, OLS variance formula. Okay, so if you know the formula of heteroscedasticity, you can actually improve the efficiency of the estimator by transforming the model, to eliminate the heteroscedasticity. Okay, so this is a useful result, but in practice, a lot of times the exact form of heteroscedasticity is not known, and so people oftentimes just use the robust standard error formula. Okay, so now we'll look at another topic with regard to ordinary least squares estimation, okay? And that's the problem of omitted variables, okay? So a lot of times we might have an idea of what variables belong in the regression, but in practice you might be missing some of them. Okay, and this is oftentimes because of a measurement issue, that you just don't have everything you'd like to have. So a classic example where you can have an omitted variables problem is when you estimate what's called the return to schooling. Okay, in that example, y is log earnings of an individual, x is the number of years of education, and z is the ability level of the individual, which is not directly observed. Okay, so beta is often called the return to education. It gives a percentage increase in earnings from one additional year of schooling. And that's because when y is measured in log, then the change in log corresponds to a percent change, okay? So there are literally like probably thousands of papers trying to estimate the returns to education. So there's a very big literature in labor economics concerned with this parameter. So, why are people so interested in this? Well, it's used to justify policies to subsidize education. Like, suppose that the return to education is 15%, but a lot of people are not going to college, or, so then you might think, well, why are people not going even though the return is so large? And so then maybe it's because there are liquidity constraints and people are unable to get loans to be able to finance this investment, which would have a big payoff. And so we might use that information to justify like a student loan program, for example, okay? Or sometimes people estimate returns to education for different groups, like for minority groups or lower income groups, and then they might allow the return to education to differ by gender, to differ by like socioeconomic background, and then maybe look if some groups have higher returns than others, and why are they not taking advantage of these high returns? Okay, so that's just a little background as to, why is there this huge literature seemingly obsessed with returns to education. Okay, now the idea is that an individual's earnings depends on years of schooling as well as ability. Okay, but many data sets do not have measures of ability. Okay, so usually ability would be an omitted regressor. And how might this cause problems? Well, you would think that higher ability people would get more schooling, okay, because for them, it's just easier to go to school. So think about, like, if you're higher ability, it's easier to learn. So the cost of schooling also tends to be lower. And so then if you observe that there's a premium, like an earnings premium for schooling, part of that premium could be ability. But if you don't see ability, then you might wrongly attribute all of it to schooling. Okay. All right, let's look at the consequence of omitting data on Z when you estimate the regression. Okay, suppose you estimate this model, which leaves out the data on Z. Is alpha going to be a consistent estimator? That's the question. Or under what circumstances could it be a consistent estimator? Okay, so just write down alpha. Alpha hat is just going to be x prime x inverse x prime y. Put in for y this equation. Okay, so you get beta. So beta is this parameter that we're interested in. Then you get x prime x inverse x prime z gamma plus x prime x inverse x prime u. Okay, so x prime x inverse x prime z gamma, notice that this is the regression coefficient that you would get if you ran a regression of z on x. Okay, so that would tell us how is schooling related to ability. Because remember, z is ability and x is years of schooling. So if we regress z on x, this would be the regression coefficient. And then gamma here is telling us how important is z in the y regression. Okay, so if we look at the probability limit of alpha hat OLS, okay, these are the terms that you'll get. So taking the p-lim, right? So all I did here is divide by 1 over n and divide here by 1 over n. And since this is inverse, it's basically like multiplying by n and dividing by n. So note that sticking these 1 over n's in here is not really doing anything. It's like multiply by n divided by n. Okay, so to each of these terms, we can apply the weak law of large numbers and the Man-Wald theorem. So the Man-Wald theorem was the p-lim of a continuous function is a continuous function of the p-lim. Okay, so we're going to say that this, by weak law of large numbers, converges to this, and Man-Wald theorem to take the inverse here. Okay, this summation converges to the expectation, and this summation here converges to the expectation. Okay, so this term is going to converge to 0. Okay, but this term will not in general converge to 0 if x and z are related. Okay, so alpha is going to generally be inconsistent if e of xi zi prime is not equal to 0. Okay, oh sorry, if z and x were not related, okay, like suppose ability and schooling had nothing to do with each other. So z, I mean, actually, I think this should be x does not explain z, because it's really, this is like the regression of z on x, okay? But you can see that if this were 0, there would be no bias, but if this is not equal to 0, and in general, we would expect this to actually be positive, right? We would expect this to be positive, and we expect that ability has a positive effect on earnings. So we would think that alpha hat OLS is probably upward biased. Okay, in this case, you have a good idea of the sign of the bias, right? Sometimes you can sign the bias just through reasoning, and sometimes not. But in this case, we have reason to believe that alpha hat OLS will be upward biased. Okay. All right. Yeah, so now, okay, that's actually it for this section. I should have a heading here, but so now we're going to start a different topic. Okay, so this is basically omitted variables bias, right? Later on, we're going to look at ways of dealing with omitted variable bias. And the main way we're going to look at is instrumental variables. Okay, but that'll be in chapter 11. Okay, now let's look at another topic related to the OLS model, which is measurement error. Okay, sometimes we have reason to believe that variables we're using may be measured with error. And this could be either because of reporting errors, that people are just reporting things slightly incorrectly, or recording errors. That somehow the way we record the information leads to some error. Okay, people may not accurately report their earnings, their education, their height, their weight, depending on what your analysis is. There are many different situations where you might think people, may not accurately report things. And there are two types of measurement error that we're going to look at. One is measurement error in the dependent variable, and one is measurement error in the independent variable. And in reality, you could actually have both. Okay, but we're going to look at them separately just to kind of minimize confusion. Okay, so suppose we have measurement error in the dependent variable. So the model is y equals x beta plus epsilon, but we don't see y. We see a noisy measure of y, which we'll call y star. Okay, so suppose y is earnings, and people report their earnings with some error. Okay, that's the idea. Okay. So look at your beta hat. We're going to plug in y star instead of y. Okay, so y star is y plus u. Okay, so you see that you get this additional term because of the measurement error. So is beta hat an unbiased estimator? Well, I mean, it depends. So if the measurement error, is not correlated with x, so if E of u given x equals 0, so it's mean 0 measurement error, and then this is the usual assumption, E of epsilon given x equals 0. Then if we look at the mean of the beta hat, we can write it this way. So here I'm applying law of iterated expectations to write it this way. I get these two terms, and if these two things are equal to 0, this equals 0, and this equals 0, then you see that it is unbiased despite the measurement error. Okay. It would not be unbiased if the measurement error were somehow systematically related to x. Okay, you can see that. Like if this were not equal to 0, then of course that would cause problems. So assuming that it's like a purely random measurement error, that's called a classical measurement error assumption. Okay, now look at consistency. So we showed it's unbiased, but remember bias is different from consistency. You could have an unbiased estimator that where the variance is not going to 0. So there are some examples of things that might be unbiased but not consistent. So it's good to analyze separately these two things. So if you take the limit as n goes to infinity, right, so apply the law of large number, weak law of large number here and here, apply Man-Wald theorem. And if this, now we apply law of iterated expectations, because we write this as E of ui given xi here. This is going to equal 0, this equals 0, right? So the p-lim of beta hat equals beta. So it's unbiased and it's consistent. So measurement error in y does not cause a huge problem, okay? Now, what about measurement error in x, okay? Well, it turns out that's a different story, okay? Measurement error in x can cause problems, okay? So let's look, how this happens. So y equals x beta plus epsilon. Now we're assuming we don't see x directly, we see x star, where x star is x plus u. Okay, and we're going to assume that this is, again, just pure random measurement error, so it's not related to the x. Also the epsilon, not related to the x. And we'll assume that the epsilon and the u are also not correlated. So they're both mean 0 and they're not correlated with each other. Okay, so now let's look. So consider the OLS estimator where we use x star instead of x. Okay, so you have to, wherever you see x star, put in x plus u. Okay, and where we see y, we'll put in the true model for y. And then you just multiply these things out. So x prime x, u prime x, plus x prime u, plus u prime u. Okay, so you get all these different terms, x prime x beta, u prime x beta, x prime epsilon, u prime epsilon. Okay, oh, sorry. Then here we divide through by n, okay, which again is innocuous because we're basically multiplying by n because there's an inverse here, and then dividing this by n. Okay, so notice that doesn't do anything to divide through by n. The reason for doing that is just to apply weak law of large numbers, okay? So this goes to e of xi prime. This here is going to go to e of ui xi, and then using law of iterated expectations, this equals 0. So this equals 0, or goes to expectation that equals 0. This goes to expectation equals 0. This goes to expectation equals 0. This does also, and this does. Okay, so the only terms that are non-zero or go to something that's non-zero is this, and this. Okay, those three terms. This here is going to go to the expected value of ui squared, which is sigma squared u. Okay, right, these terms go to 0. So p-lim of beta hat equals this. Okay, so you can see if sigma squared u were 0, there would be no bias. Okay, but in general, this is going to be bigger than 0 because we know variance has to be positive, which means that beta hat, I mean, this multiplied this by this term is a number less than 1 if sigma squared u is positive. Okay, so it means that beta hat has a tendency to be too small, because we're multiplying the beta by a number less than 1. I mean, it's not, I guess, it's not strictly speaking downward bias because if beta were negative, we're multiplying it by a number that's less than 1. Okay, so it kind of shrinks the beta in magnitude is what I mean here. See how this is going to be a number less than 1. Okay, so what are some methods we have for dealing with a measurement error bias problem? So I'm going to talk about 2 different approaches. One is instrumental variables. Okay, and actually this should say chapter 11. So chapter 11 is all about instrumental variables. So this is just kind of a preview, okay, because later on we're going to cover this in depth. So suppose you have the model given above, right? And well, I guess you can write it in this way. So you have basically y equals x beta plus epsilon, and then we're going to add x star beta and subtract x star beta. Okay, that's like adding 0 basically, because you add it and subtract it to the original model. Okay, that lets you write it in this way. Okay, so you can see that the measurement error problem, basically you have this composite residual term. Okay, and then there's an endogeneity problem because E of ui given x star is not equal to 0. Because remember, x star is x plus u. So u is part of x star. And so therefore, this error term is going to be correlated with the x. So suppose you have some variable, w, that is correlated with the true x, but not with the measurement error. Okay, so we need some w that's correlated with the x star, but not correlated with u. Okay, might be hard to come up with an idea of this variable, but that's that's the kind of information you'd need. Okay, so consider this estimator. So this actually is what's called the IV estimator. Okay, w prime x star inverse w prime y. And dividing by n, both sides, we can write in this way and plugging in for y. Okay, now if we apply law of large numbers, take the p-lim. Okay, w's uncorrelated with u. So this goes to expectation, which is 0. Okay, and this is also 0 by assumption, goes to something at the expected value 0. And so the p-lim is beta. So if you have an instrument which is correlated with the original x, but uncorrelated with the measurement error, then you could use that to get a consistent estimator of beta. Okay, but the next chapter is all about this, so if it's not clear from this brief introduction, I think the procedure will become clear in chapter 11. Okay, now here's another approach for dealing with measurement error problems. Or actually, this is not for measurement error. The IV is for measurement error. This is for omitted variables problems. Okay, so this chapter has a lot of different approaches. So let's just kind of go back and review because we've done a lot of different things in this chapter. Okay, first topic was heteroscedasticity. Second topic is omitted variables. Third topic is measurement error. You can have in the dependent variable or in the independent variable. Okay, instrumental variables is one solution to the measurement error problem. Okay, so now we're going to look at within estimators, which is one solution to the omitted variable problem. Okay, so this is not for measurement error, this is for omitted variables. Okay, so what are within estimators? Actually, the idea of these estimators is very intuitive. So let's go back to the example where a researcher wants to estimate the returns to education. So remember, that's the coefficient on years of schooling in an earnings regression. And assume that the researcher has data on identical twins. Okay, so I and J represent two twins, and let SI and SJ be their schooling levels. Okay, and let AI and AJ be their ability levels. Okay, so remember, ability is not observed. What we're going to assume is that for identical twins, that ability is the same. Okay, so we'll basically assume AI equals AJ. Now, how does this help us out? If ability is unobserved, but it's the same across twins, then we can eliminate the effective ability. So we can basically get rid of the ability in the regression by taking the difference between twins within the same family. Okay, so take yi minus yj equals beta times si minus sj, and you see under the assumption that ability is the same, that drops out. Okay, and so the idea of the within estimator is that you just apply the standard OLS estimator to this differenced equation. It's called a within estimator because we're using variation in the regressors within a unit. So in this case, we have variation across two different twins within a family. Okay, note that this procedure would not work if SI equaled SJ for everybody. Okay, so you need to have that there's some differences in the schooling levels that twins get, but that twins have the same ability. Okay, and this strategy has actually been used. There are a bunch of studies of twins trying to get the returns to education. Sometimes people do this procedure using siblings, like not necessarily identical twins, but still assuming that ability is roughly the same across siblings within the same family. Another version of this estimator that would also work is you could take the mean, instead of differencing between the two twins, you can just take the mean of the y. Then using the original equation, you take yi minus the mean, okay? And that's another way of eliminating a, because ai equals a bar when all the kids within the same family have the same ability. So this is taking the mean within the family. So if you had like two twins, you take the mean for the two twins. Or if you use siblings, you could take the mean across all siblings. Okay, so you end up with this difference regression. All right. So if you have two units, whether you do a within estimator by taking differences or whether you do just the means is going to be identical. Okay, you'll get the same numbers if you do it either way. Okay, actually this twins idea was something that was developed at Penn. Jerry Behrman, who's on our faculty, he wrote one of the very first papers using twins where they implemented this idea. They were following a data set. There's some data sets on twins, like Minnesota has a nice data set on twins. There's also a data set collected in Twinsburg, Ohio, where they have a twins convention. That was something that I think Angrist and Kruger collected. So they have a couple papers. And then a lot of Scandinavian countries have very detailed information basically on everybody within the country that allows you to follow data on twins as well. Okay, so this concludes all the topics for this chapter. So this is a longer chapter with a few different topics. All right, signing off.